Hey everybody, it's Monday, May 17th, and as you can see here in the aim today, our goal for today's video is to review the free response question that was assigned on Monday. I like this question. It's weird. There's a lot of little tricks that you have to employ to be able to answer this thing correctly. There's a lot of different possibilities, and so I thought as one of the last experimental design questions for us to look at, since we really haven't looked at just like a straight up motion one in a while, this would be a pretty good example. This question here says a student in a physics lab has a block with a fan attached to it, shown in the figure above. It says the fan is a pivot, so that the angle theta it makes with the horizontal can be adjusted between 0 and 90 degrees. When the fan is pointed horizontally so that the angle theta equals 0 degrees, the block accelerates from rest along a track, even though there is friction between the block and the track. For the following questions, assume that the student has access to equipment that would usually be found in a high school physics laboratory. Now, the first thing that we should probably mention here is that they tell us when the angle is 0, the block accelerates from rest along the track, even though there is friction between the block and the track. So I guess the main question we're going to want to ask and answer here is, what does that mean? What does it mean that the block accelerates from rest along the track when the angle is 0? What that tells you here is that if you take MA, the net force, and you set it equal to the sum of the forces, that would be equal to the force from the fan minus the force of friction, that the force from the fan here would be larger than the force from friction. That's an important thing to realize here. This thing on its own can exert a force that is larger than the force of friction. Now, the reason I bring that up is because that should inform your answers to the later parts of this question. Now, the first part of the question here says, describe an experimental procedure that the student can use to measure the force F that the air exerts on the fan block system when the fan is turned on. Now, if you thought that was kind of weird that it says that the air exerts on the fan block system, it's important to realize Newton's third law is at play here. The fan spins, it exerts a force on the air, and by Newton's third law, if the fan exerts a force on the air, well, then the air exerts a force on the fan that is equal and opposite. Now, it says here, assume the magnitude is the same for all angles theta. The first thing it asks you is which quantities would be measured. Now, the scoring guide shows all of these parts, 1, 2, and 3 for part A. Notice which quantities would be measured is only part 1. So I'm going to kind of just run through my procedure, and then I'll show you the scoring guide, and we can talk about some of the other possibilities. For the answer to the question, what quantities would be measured, what I decided to do was take the simplest approach. The reason why I say this is the simplest approach is because you have some complications with this kind of problem, because there's friction. And so if you just tried to have the block accelerate along the track, and let's say use a motion sensor to measure the acceleration, that's not measuring the force exerted by the fan. It would be allowing you to measure the net force, which is a combination of the friction force and the force from the fan. So what I said here was, in order to determine the force exerted by the air on the fan block system, we can measure the downward force exerted on the fan block system when the fan is turned off and when the fan is turned on. Now, part B of this question said, what equipment would be used for the measurements? Include a labeled diagram of the setup, talking also about how the equipment would be used. So I said here, in order to measure the force that the air exerts on the fan block system, we could use a force sensor or a spring scale. So I would use the force sensor, which, remember, can have a hook attached to it. And I would basically just attach the fan with the fan turned straight up like this. Notice this method exploits Newton's third law because the force exerted by the fan on the air is equal and opposite to the force exerted on the air by the fan. So I'd basically just turn it up and measure it like this. Notice I said I would do that when the fan is off and when the fan is on. That's an important thing to realize. Moving on to part A3, it says describe the overall procedure to be used and give enough detail so a student could replicate the experiment. What I said here is, in order to measure the force exerted by the air on the fan block system, we can orient the fan straight up at an angle of 90 degrees from the horizontal and hang it from the hook on the force sensor. When the fan is turned off, the force sensor will give a constant reading, which will be equal to the weight of the fan block system. When the fan is turned on, the force sensor will also read a constant force reading, which will be larger, which will be the total downward force on the fan block system. We can do this multiple times and average the values together, and the difference between these two will be the downward force exerted by the air on the fan. Now, if you remember my lab video where I showed you how all these sensors could be used, in the program, I think it's called Vernier graphical analysis, you could zero out the reading on a force sensor. So if you hang the fan from the sensor, it's going to read a value, but you could hit 0. And basically what that does is it tells the sensor, this is the new 0. Measure all forces relative to this. That's an important thing to realize. This is a little bit of a bizarre method here, but it works based on the constraints of the problem here. So we're basically just turning the fan up. The downward force of gravity is the weight. Of course, when we turn the fan on, it blows air up, so the air pushes on it down, and that increases the force sensor reading. That, of course, is the combination of the weight and that force from the air, which act in the same direction, so they add. So if we just subtract off the weight from the total force, we got our force right there. Take a second to pause this video here and write that down. You hit play, move on to the scoring guide. All right, moving on to the scoring guide here. Now you'll see why I just did those all quickly before I showed you the scoring guide. It says parts 1, 2, and 3 are read together. You get 1 point for measuring the mass or weight of the relevant system, and you get 1 point for making a measurement of force, or something from which a force can be calculated, with a fan turned on. It says here, note, fan angles of either 0 or 90 degrees need not be measured directly, since these are given as the minimum and maximum angles possible. If the procedure involves intermediate angles, then these angles must be measured. Example 1 is showing basically the method that I just proposed. It says here also there's a variant with example 1A in parentheses. So they're measuring the downward force exerted by the fan block system, or mass if you just throw it on a triple beam balance. You could use a spring scale, force sensor, or a mechanical balance. And you could set the fan angle to 90 degrees with the fan off, hang the system from a spring scale to find its weight, or place it on a triple beam balance to find its mass. Turn the fan on and record the force from the spring scale or mass reading for the mechanical balance. Same idea here. The difference between the two gives you your force reading. Now, I'm going to keep this on the screen for a second. So if you want to look at this, go ahead and pause this video here. But there's a second method, which even if you talked about this method, I think is worth it to pay attention to for the test. So take a second to pause this video here and make sure you understand all aspects of the scoring guide. And when you hit play, we'll move on to the second part of it. Now, the second part of this scoring guide has a second example in it, which I almost thought was kind of shocking. But it's a nice little cheat almost to get around the issues in this problem. Notice you get 1 point for measuring mass or weight and 1 point for making a measurement of force, or something from which force can be calculated with a fan turned on. There are a lot of ways you could do this, but as I mentioned, the big complication here is that you have friction between the block and the track. And so if you just turn the fan on and measure its acceleration, using the slope of a velocity versus time graph, you're not calculating the force exerted by the fan, you're finding the net force. So look at what they did. They said their example is to measure the mass of the fan block system and a low friction cart, and the velocity of the cart as a function of time. They're going to use a scale or triple beam balance to measure the mass, and a motion detector to measure the velocity as a function of time. And they just take the fan block system and just put it on top of one of those carts I was showing you in that video. That's a low friction cart. They figure out the total mass by putting it on a triple beam balance. Then they just pop it on the track, where now you've basically just totally avoided the friction problem that we had with this thing. It's just sitting on a low friction cart, and it can move with no friction from there, or at least very minimal friction. And so it says here, now that you do that, you set the fan angle to 0, you turn on the fan, you release it from rest, and you use the motion detector to graph the cart velocity as a function of time. If you take the slope of that, you got your acceleration, and then bing, bang, boom, you're done. F equals ma. That's genius. And I think it's important to realize, if you're feeling like you're really stuck on the AP test and you need a Hail Mary, well, then this is it. You can always take something and just pop it on a low friction cart, apparently, and get around the issue that friction presents to this kind of problem. Take a second to pause this video here and look that over, making sure you understand all aspects of what they were looking for and how it pertains to the scoring guide. And when you hit play, we'll move on. All right, moving on to the next part here. Part A4, which has a separate section of the scoring guide, says describe how the force can be determined from the measurements described in A1 through 3. So I think it's always good to look ahead because notice I did kind of describe how the force can be determined from the measurements. I think if you are looking at all of the parts of a question to an experimental design before you answer it, then you can save yourself time by not having to like unnecessarily repeat things. I spent time in my explanation saying, you know, the difference between the two will be the downward force exerted by the air. I didn't have to say that. And now that I got to this next part, basically I just got to say that again, and that's a waste of time. What I said here was in order to determine the force exerted on the fan by the air, we can subtract the reading on the force sensor with the fan on and the reading on the force sensor with the fan off. This value will be equal to the force exerted on the fan by the air. Now, I would imagine if you just said, we're going to hang the thing and we're going to measure its weight and then we're going to zero out the force sensor, and then you went through and explained all that again, they would have to give you credit for that because it is correct. But I think it ends up being like a little too much. And it's easy enough to just say, well, we could subtract them and that's that. That's not that hard. If the force sensor shows 40 with the fan off and then it shows 50 with the fan on, well, then it's 10 newtons from the fan. That's pretty basic, I think. Take a second to pause this video here and write that down. When you hit play, we'll move on to the scoring guide. All right, moving on to the scoring guide here. Notice this part was only worth 1 point, and it says for correctly indicating a method to determine the force exerted by the air on the fan using the measurements and procedure from parts A1, 2, and 3. So for example 1, the example I used, they just said take the difference. It's pretty easy. Of course, if you have a mass method, you just literally measured the mass when the fan was on and the mass when the fan was off using a triple beam balance, then you have to multiply it by G. And this difference is the force exerted by the air on the fan. Example 2 is nice, though. It's smart. It's interesting. You can estimate the average slope of the graph, which is the acceleration. And I think the fact that they say estimate is kind of weird. You saw, or you should have seen if you watched that lab video, that the velocity versus time graph can easily be analyzed to give you the slope of the line of best fit for that. So the slope, of course, because it's a velocity versus time graph, is the acceleration. And then, of course, you just use F equals ma with the masses plugged in to find the force exerted by the air on the fan. Of course, if you have the fan block system sitting on top of a low friction cart, then you have to use the mass of the fan block system plus the mass of the cart. Take a second to pause this video here. Make sure you understand all aspects of the scoring guide. And when you hit play, we'll move on. Now, the second reason why I think it is smart to go ahead and look at all parts of an experimental design question before you actually start to answer it is because of this part. Because when I first saw this question, I went, oh my God, what a nightmare. They really want them to do this experiment where they first have to talk about how they have to measure the friction force just to figure the fan force. That was honestly the first thing that came to my mind. Then I realized, oh yeah, well, you could just hang it if you had to, but like, that's kind of weird. I never would have thought of that low friction thing. That's why I wanted to show you that, because I think that's interesting. But I think it's important to realize you could have, in that first part of the experiment, said, I'm going to do an experiment where I'm going to measure the coefficient of friction, and then I'll have the friction force, and then I'm just going to set the angle to 0, and I'm going to measure the net force. And then the net force is equal to the difference between the fan force and the friction force. And I'm going to use that to calculate the fan force. That's too much, especially because you would have to write all of that again in this part. And so they wanted you really to do this getting around friction in the first part. Now you got to measure the coefficient of friction. So in order to measure the coefficient of friction here, you got to think, well, what's in the friction force equation? Remember, the equation is key for an experimental design. You got the friction force equals the coefficient of friction times the normal force. Again, the first 3 parts of this are scored together, so I'm just going to zip through it. In order to measure the coefficient of friction between the block and the track, we must measure the fan block system's velocity, the mass of the fan block system, and the angle at which the fan is tilted. The velocity, the mass, and the angle. Now, of course, the next part says, what equipment are you going to use and how would that equipment be used? Include a labeled diagram of the experimental setup. I wrote here, in order to measure the coefficient of friction between the block and the track, we must measure the fan block system's velocity, the mass of the fan block system, and the angle at which the fan is tilted. We can measure the velocity with a motion sensor, the angle at which the fan block system is tilted with the protractor, and the mass of the fan block system with the triple beam balance. So they wanted us to include a diagram. So you could put the motion sensor at the end of the track. Here's the track. We could put like a little side thing with a triple beam balance here. So we could just write scale and draw the stupid thing on top of the scale. And then here we can have this thing sitting on top of the track. We could draw our little fan here. We can have a little protractor. There's our horizontal. And that's pretty much it. Now, part 3, of course, like it was for the last one, says describe the overall procedure to be used. Again, there's more than one way to do this. As you're going to see here in a minute, the scoring guide actually lists 5 possible options for how you can perform this procedure. There are a lot of ways that you can do this. That's an important thing to realize. The first thing we should say here, and I think this is going to be advice that you should remember for the test because this is something I would have heavily emphasized in class, you would like to put this system in a position where it is able to move at a constant velocity in friction experiments. I think it's really important to realize in almost every situation, you cannot directly measure the force of friction. You just can't. You have to measure something else that will enable you to determine the force of friction. So here's the deal. If you put the fan block system in a situation where it is able to move at a constant velocity, then simply by measuring the applied force, you will measure the friction force. Now, the clutch thing about that is we already measured the applied force from the fan in the first part. That's a really important thing to realize for this experimental design question. So in this part here, part 3, which says describe the overall procedure to be used, this is what I wrote. I wrote first, we must measure the mass with a triple beam balance. This will help us determine the normal force. That you should have realized. We can, using the motion sensor and the protractor, determine the angle at which the fan must be tilted to allow the block to move at a constant speed, which we could tell when the slope of the velocity versus time graph is 0. This ensures that the force of friction must be equal to the x component of the applied force, which we determined in part A. The normal force, if the fan is tilted upward, is the sum of the weight of the object and the y component of the applied force. So notice here, yeah, we had to tilt this thing at an angle to make the thing move at a constant speed, but now we have simplified in a lot of ways some of the other issues we had. Now, you can make any argument you want, and obviously this is up to personal preference, but I think this is the smartest way to do this. Take a second to pause this video here and write that down, and when you hit play, we'll move on to the scoring guide. All right, let's take a look at the scoring guide. There's a lot on here. It says, notice the first 3 parts to this question again, or this part of the question, are read together again. You get 1 point for describing measurements that would allow determination of the acceleration, and 1 point for describing a procedure that is practical / feasible in a school laboratory. Very vague. It says here also, note in parts B, 1, 2, and 3, it's acceptable to say the same as in part A with the following changes, with the changes to the procedure in part A then listed. Now, I think this way is much better. So it says here first, place the fan block on the track with the angle equals 0. Place a motion detector behind it, set to graph velocity versus time. Turn the fan on and release it from rest. Repeat the procedure several times. For the next example, it says place the fan block on the track with the angle equal to 0. Place a photo gate just in front of the block and a second photo gate 1 meter or 2 in front of the block. Measure the distance from the front of the block to the front of that second photo gate. Turn on the fan and release the block from rest. The photo gates measure the time it takes the blocks to travel the measured distance to the second photo gate. This method is going to have you using equations to do calculations of the acceleration. That's a nightmare. I would avoid that. Example 5 says to measure the angle of the fan, the velocity of the fan block system is a function of time, the protractor to measure the angle, and the motion detector to measure the velocity versus time. And it says adjust the fan angle until the fan block slides with a constant speed after being given a push. Use the motion detector to determine whether the speed is constant. 0 slope on a graph of velocity is a function of time. That method, I think, is superior. Makes it a lot easier to talk about the analysis part, in my view. Take a second to pause this video here and write that down, making sure you understand all aspects of the scoring guide. And when you hit play, we'll move on. All right, moving on here. I just want you to write down this note. I think it's really important. I think it really might come in handy for the test. It's a really smart idea to put an object in a situation where it can move at a constant velocity when measuring friction coefficients or friction forces if possible. This will ensure that the applied force in the situation, which you can measure with a force sensor if you have to pull the object, is equal to the force of kinetic friction. Obviously, the same is true if it's not moving, if you have to measure the force of static friction too. This goes back to that whole idea of the drag test to measure forces or coefficients of static friction. Take a second to pause this video here, write that note down. This is really important. And when you hit play, we'll take a look at part B4. All right, looking at part B4 here, it says on the dot to the right, which represents the fan block system, draw and label the forces, not components, that are exerted on the system during the experiment described in parts B1 through B3. Represent each force by a distinct arrow starting on and pointing away from the dot. Now, the first thing to be realized here, I think, is that there are a lot of different ways that this diagram can be shown. I'm going to show it from mine. I think the first thing to realize is that in order for the fan to move at a constant speed, the fan is going to be pushing air up, which means the force exerted by the air on the fan is going to be tilted down at an angle like this. Now, because that force has a vertical component that is down, that means it's pushing the block into the surface more, which actually means the normal force is going to be bigger than the weight. It's going to be the sum of the y component of this force and the weight. And then, of course, we're going to have friction acting on this thing, which should be shown as being smaller than the normal force, which it is here, and so that's fine. Take a second to pause this video here and write that down if this was the example you used, and when you hit play, we'll move on to the scoring guide. All right, moving on to the scoring guide here. This one was weird. They only gave 1 point, and it just says for correctly drawn and labeled vectors for the force exerted by air on fan and for the frictional force exerted on the block by the track corresponding to the experiment that you described in part B3. Other forces correctly drawn and labeled, and no incorrect forces corresponding to the experiment described in part B3. Basically, they just wanted correct diagram for whatever you drew. I think that's kind of weird. Notice here for examples 3 and 4, where you're just going to keep the thing horizontal, have it accelerate and measure the acceleration from a motion sensor. The fan could be positioned horizontally, and so that's what they did. They just showed it horizontal. They showed the friction force in the other direction smaller because it's accelerating. So in this situation, the friction force should be smaller than the implied force. And then because the fan is just horizontal, the normal force is equal to the weight. This is the one that I just drew. The fan force now is down at an angle, so the normal force is bigger than the weight. And then, of course, the x component of the force is equal to the friction force, or at least roughly. Take a second to pause this video here. Make sure you understand all aspects of the scoring guide. And when you hit play, we'll move on to the next part. All right, moving on to the next part here. It says, describe how to analyze the data from the experiment described in parts B1 through 3 in order to determine the coefficient of kinetic friction between the block and the track. Your analysis may include the force F exerted by the air on the fan block system. Do not add to the free body diagram that you already drew in that previous part. So you already know what my experiment looks like. Here's what I wrote. First, this method requires the object to move at a constant speed, which we can ensure is the case if the slope of the velocity versus time graph produced by the motion sensor is equal to 0. Since the coefficient of friction is equal to the quotient of the friction force and the normal force, we must obtain values for the friction force and the normal force. The friction force here is equal to the applied force opposite of the direction of the friction force, so this would be the x component of the force exerted by the fan, as given by the equation Fx equals F fan cosine theta. The normal force, since the force exerted on the fan block system has a downward y component, is equal to the sum of the weight and the y component of the fan block system force. Fn equals Fg plus F fan y, that looks weird, which is equal to mg plus F sine theta. The coefficient of friction can then be determined by dividing those two values. Notice in this particular circumstance, that would end up giving you an equation that would say the coefficient of friction, mu with the subscript k, is equal to F from the fan times cosine theta over mg plus F from the fan times the sine of the angle theta. And there you have it. Take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, moving on to the scoring guide here. Again, there's a lot. They get 1 point for using kinematic data to obtain acceleration, A, or showing that A equals 0. It says alternatively, the point can be earned using the work energy solution with kinetic energy K equals 1/2 mv squared. I don't know why you would ever do that, though, so just like forget that noise. Then it says for relating the frictional force and the coefficient of kinetic friction as the friction force equals coefficient times the normal force. 1 point for correct representation of the normal force, correctly referring back to a measurement of the fan block system. So that would be Fn equals mg if the angle is equal to 0, or Fn equals mg plus f sine theta if the angle is equal or not equal to 0. Notice here it says plus here because it has to be, because if you go back to the original picture here, the fan can only be tilted up. And that means that the normal force can only be added to with that y component. And then 1 point for using Newton's second law consistently with the normal force above for the appropriate forces or force components in the direction of the fan's motion that would lead to the determination of the coefficient of friction. That could just be F net equals ma. That could be the friction force, the force from the fan minus the friction force equals ma, or the coefficient equals the fan force minus ma over mg if the angle is equal to 0, or the coefficient of friction is equal to the friction force cosine theta minus ma, then over mg plus f sine theta. Of course, here, if the acceleration is equal to 0, because we have the thing moving at a constant speed, that part will disappear. Notice here, then it says, alternatively, the point can be earned using the work energy solution that would lead to the determination of the coefficient of kinetic friction. You could do that, I guess. You could turn the fan off and see how far it goes before it stops, and then use work energy theorem with the stopping distance. I don't really see why you would ever do that. So there you have it. Take a second to pause this video here and take a good look at the scoring guide, making sure you understand all aspects of it. And when you hit play, we'll move on to the examples. All right, moving on to the examples here. Example 3 said the angle is equal to 0. Determine the slope of each velocity versus time graph to get an acceleration for each trial and average them together. Call this the average acceleration A. The kinetic frictional force exerted by the track on the block is mu mg, where m is the mass of the fan block, is found in part A. Since the acceleration is purely horizontal, and since the normal force and mg must balance, and so they said here, so by Newton's second law, letting F denote the force exerted by the air on the fan found in part A, we get F net equals ma. F net, of course, is the fan force minus the friction force equals ma. So that'd be F minus mu mg equals ma, and then we divide by the coefficient of friction after we move everything around to get mu equals F minus ma over mg. Example 4 says the angle theta equals 0, and so we have the distance d denoting the distance from the block to the second photo gate, and t corresponding to the time. The initial velocity is 0, so d equals 1/2 at squared, and then they solve for the acceleration using 2d over t squared. For each trial, calculate that acceleration and then take the average, which becomes our best estimate of A, and then the rest of the solution is we'll use F equals ma, we have the difference in the applied force and the friction force, and we solve it for mu. That's crazy town as far as I'm concerned. This one is so simple. We say the acceleration is 0, the net force in the horizontal direction is 0. That means the friction force is equal to the applied force. And then, bang, we solve for the coefficient of friction using this equation. I thought it was totally weird that they even mentioned here that the acceleration is 0, and then they included it in the equation. 0. Get out of here. So it's just F cosine theta over mg plus F sine theta. I think that's way easier. Judge it for yourself. Take a second to pause this video here. Make sure you understand all these examples. And when you hit play, we'll move on to the final part. All right, the final part here says, in a different experiment, the student attaches the block to the top of a low friction cart. On the axes below, sketch a graph of the work done by the air on the fan block cart system as a function of theta when the system travels a fixed distance d. The work done as a function of the angle. Well, what is the equation for work? It's F delta x cosine theta. That's the key here to this problem. The work is directly proportional to the cosine of the angle. Well, what do we know about the cosine? We know when the angle is equal to 0 degrees, the cosine is equal to 1. And we know that when the angle is 90 degrees, the cosine equals 0. So we know this thing has got to start up here somewhere and then end up down here. What exactly is it supposed to look like, though? It's supposed to look like a cosine graph, but only up to 90 degrees. So it'll look a little something like this. That's not horrible. Of course, you could probably draw this a little better if you have a piece of paper in front of you using a ruler, maybe as you like sort of rotate through the ruler. But if you're not exactly sure what it should look like, it's important to remember you can just go to your calculator. Now, for some reason, my calculator emulator is not working. But if you just graph cosine of x and you make sure your calculator is in radians, then it will show you what the cosine graph should look like. The important thing to realize is that this is just going to 90 degrees. 2 pi radians, it's important to remember, is 360 degrees. So 90 degrees is 2 pi radians divided by 4. 2 pi divided by 4 is 1.57, which means that's just going to be up to here. Notice if we actually go ahead and select that, it'll show us that's pi by 2, or 90 degrees. And so we're going to see it start like relatively horizontal here and then curve down. That's it. Taking a look at the scoring guide, it says the correct graph shows the work done is proportional to the cosine of the angle. For showing a curve that continually decreases from a maximum value at 0 degrees to a minimum value of 0 at 90 degrees. And then 1 point for a curve that is concave downward, for all of you calculus kids, that has a negative second derivative. Ooh la la. Take a second to pause this video here and write that down, making sure you understand all aspects of the scoring guide. And when you hit play, we'll move on. All right, everybody, that is it for today. I decided to make this video separate from the multiple choice assignment video, just so you had them all in 2 pieces and you didn't need to scroll all over town. And so with that, that's it for the experimental design question. Was this one difficult? Of course it was. I think this is one of the more difficult experimental design questions that they've ever given. But I think there's a lot of nice little tips and tricks that are worth it to keep in your back pocket as we prepare for the AP exam. That's it, everybody. 1 week. Keep working. We're almost there. Take it easy, everybody.